The next speaker is Jerome Karle. I'd like to claim him as a student, but the evidence doesn't support that. Jerome. 40 minutes altogether.
Yes. Well, on the basis of the introduction, I think this is coming home time for me. Although I'm a little old for it, I've always regarded Dr. Pauling as my scientific grandfather. And the reason for that is actually quite straightforward. As Dr. Pauling mentioned, Lawrence Brockway, who was my mentor, was the first, or if not the first, one of the really early graduate students of Dr. Pauling. And Isabella and I were, except for one person, the first graduate students of Lawrence Brockway. So I think the connections are quite close. I'm sure that Lawrence Brockway learned quite a few things from you, and we learned quite a few things from Lawrence. I'm always pleased to contemplate coming to an American Crystallographic Association meeting, but I must say that recently there have been issues of the newsletter that have intimidated me. Have you seen these little articles about suspect unit cells and suspect space groups? Well, borrowing a remark that George Burns once made, what I do before a meeting is collect together issues of the newsletter, and I look up these articles, various articles on various suspicions, and I look through them, and if my name isn't there, I pack my bags and come to the meeting. Well, today I'd like to talk about a development in analyzing anomalous dispersion experiments, which I'm pleased to say is beginning to take hold. There are several groups who are beginning to use it with success, and there are several structures on their way, several that have been completed. The idea is the following, namely that although there have been many, many algebraic analyses of the anomalous dispersion technique, there's a way to do it that gives you a very nice series of equations. They're exact and they're linear. And what that means, that if you do a good enough experiment, you're guaranteed that you're going to get the answer from the mathematics. In fact, they have a feature which goes somewhat beyond the original intention of multiple wavelength anomalous dispersion. Namely, I will show that you can get good answers using only one wavelength. And I will explain why that happens, even though the general dogma has been that you need two wavelengths. May I have the first slide, please? I brought a number of slides, but if we just concentrate on the first one, I can go through the rest of the slides very quickly. And I think that I will not exceed my quota. This equation is a typical one. It refers to the simplest case in which you have, let's say ideally, atoms that do not scatter anomalously, and one type of anomalous scatterer, And if we look at this equation for a while, we'll understand how all of them work, and we won't have to really bother ourselves with looking at the details of a few slides that are very messy, which are put into this lecture just to show that something really exists. The feature is, or the basis on which this particular algebraic relationship was derived, is based on the thought that instead of combining the real part of the anomalous correction with the atomic scattering factor of the normal type, that you separate both the real and the imaginary parts of the anomalous correction to the atomic scattering factor, and do the algebra that way. The consequence is that you will get, as your unknowns, intensities and phase differences that refer only to the normal scattering, and the anomalous part comes in as coefficients. And those coefficients you get by perhaps doing a little experiment yourself or looking up the tables. And so you get true simultaneous equations in which the unknowns are always normal scattering parameters and coefficients that vary with the wavelength, and you get them from the tables. So let's see if I can aim this thing. Yes. Well, this is your measurement. This is an intensity that you've measured at a particular wavelength. And in this system with non-anomalous atoms that do not scatter anomalously and one type of anomalous scatterer, you will have, as your unknowns, the intensity for the non-anomalous. Let's say that's the native protein. And the subscript 1 refers to the native material. And N means that it's normal scattering. Well, of course, that's all you have if it doesn't scatter anomalously. The second unknown is what would be normal scattering from the anomalous scatterers. And the 2 refers to that. And the other unknowns that you select to make this linear are this magnitude and this magnitude times the cosine of corresponding phase differences, and the sine function, same thing. So you have 4 unknowns. And you, of course, can measure this at the minus h, and the only difference in these equations are that you get a minus sign here. And you see this coefficient that is within the braces, and the coefficient here, and coefficient here. Those are all these variable and non-variable atomic scattering factors that you get from the tables. Now, of course, there's another equation that's very obvious that comes from sine squared plus cosine squared is equal to 1. And yes, we use that. It doesn't interfere at all with the calculation. Now, if you make a measurement at another wavelength, you already have 4 equations and really 3 unknowns because, well, I'll put it another way. You can still have your 4 unknowns, and you have the 4 equations from the plus and minus h at one wavelength, the plus and minus h at another wavelength, and then you have the additional 5th equation that says cosine squared plus sine squared is equal to 1. So with 2 wavelengths, it's overdetermined. There isn't much to talk about such a system because if you use exact data, you get exact answers. If you want to really make a study of the effect of errors, it's better to do it experimentally. So I will proceed a bit with this discussion in terms of what happens if you do things with one wavelength. Now, I don't mean to make anything mysterious. Why does it work for one wavelength? Well, the reason is this. The conclusions normally that imply that you need two wavelengths are based on looking at the bifoot pairs, the intensity with the plus H and with the minus H, and you can draw a nice diagram and with the connection between the two structure factor magnitudes, you get two different triangles. However, if you analyze it further and consider it in terms of the quantities, the intensity for the native and the intensity for the anomalously scattering atoms, why then, generally speaking, when there are big differences between the two ambiguous answers, you will get what seem to be and what are unlikely values for parameters such as this. And the experimental result, the more likely one, is the one that turns out to be correct. And so you can get quite good answers to the values for the phase differences by doing the following. You make a statistical estimate of this quantity and hold it fixed. It's not terribly accurate, but what you're after are these phase differences. And then you have starting values in a least squares calculation for this intensity, and you make a statistical estimate of that. And then you can also get, based on this one that you're holding fixed and your initial estimate of this and some other manipulations, you can make an estimate of this entire quantity and also of this one. And since you are starting with statistically reasonable values, you are much more often than not going to pull out the one of two ambiguous results that is more nearly the correct one. And that's how it turns out. Let's see, this looks like something that I can use. Don't bother with the details. This is the way it looks. If you have two types of atoms and they're both anomalous scatterers, and then this theory is complete, this is the way the systems of equations look if you have any number and any kind of anomalous scatterers. And the character of the unknowns is always the same. For each one of the types of atoms, you get a separate intensity, and for each one of the intensities, or pairs of them, you get phase differences. Now, just in passing, one of the things that you could hope to do, since you isolate the intensity for the anomalous scatterers, is to use that intensity in various ways. And this does not refer to the one wavelength experiment because the accuracy is bad. But if you have an overdetermined system, you could hope to get good values for the anomalous scatterers, and then you could think of making a Patterson function from them or doing direct methods on them in the hopes of finding the structure of the heavy atoms. And incidentally, one of the unknowns is just the difference between the native protein phase and the heavy atoms phase. And if you know that value, and then separately you know the structure given by the heavy atoms, you will then eventually just very simply be able to solve for the native protein phase. Now, in the case that you can't get the heavy atom structure for some reason, well, then you can turn these results into triplet phase invariants and try to just solve for the protein structure with triplet phase invariants. The way you do that is that, remember, an unknown is the F1H minus the, phi 2H, the phi 1K minus the phi 2K. These are three different ones. And then something that will just make this an invariant by having subscripts that are the opposite of the H plus K. And presumably you've, in this case, a multiple wavelength experiment, you have some value. The triplet phase invariant for the heavy atoms, a simple structure. If the magnitudes of the structure factor are at all large associated with these, you can set that equal to 0, and to a very good approximation then have triplet phase invariants evaluated as being essentially equal to this AHK. How am I doing? Well, this just repeats what I've been saying, so I'll go by. This is the kind of a diagram I was talking about, and the usual drawing that's made to show the ambiguity is to have an FH and an F minus H and the connection to it, and then some other one over here which shows the ambiguity. But here we've got extra things hung on, and I'd like to call your attention in particular to this magnitude that's associated with the structure factor for the native protein. And later on, I'll come back to this, and I'll show you what that kind of a construction looks like here, and you'll see why there's a difference. This is the same equation that I had before, just telescoped with the anomalous dispersion coefficients, just written as alpha, beta, gamma. But it's the same thing as I had before. Now, I did a calculation in which I did just exactly what I said. I statistically estimated the magnitude for this and held it constant. And from other statistics, got a starting value for this magnitude. But I did something else. I wanted to see what would happen if I put errors into the difference between the measured F lambda H minus the F lambda minus H. Now here, there's no error. And I had listed for cytochrome, C550, I had listed the differences in sequence. 1 to 100 are the largest ones, 9 to 100 to 1,000 somewhere along the line, 1,600, 1,700. They get smaller and smaller. Altogether, this was 2.5 angstrom data, and there were about 3,200 non-centric reflections. And here are the errors. The errors go up as the differences get smaller. But you see, this is in radians and is entirely tolerable. The interesting thing is that if you increase the difference by error 50% between the measured F intensity with H as compared to the intensity with H minus, why, the errors don't change very much. Of course, the errors in here are pretty bad. Now, at the other end, if you divide it, why, the errors are larger, but nevertheless, this is entirely tolerable. So this is just insight. The next, in this case, I just treated the platinum and the PTCl4 substituent as the anomalous scatterer. And in the next one, there are 4 different anomalous scatterers that one might take into consideration: the sulfur, a chlorine, a platinum, and an iron atom. The errors go up some, but they're still tolerable. I've completed the drawing here, and this line down here is the magnitude of the structure factor for the native protein. And this diagram would suggest that this sort of a value is more probable than this one. And it's that sort of thing that accounts for resolving the ambiguity. There was another formulation of this. Recently, Wayne Hendrickson wrote out these equations in terms of a new variable. Instead of having the F1 for the native protein, he had an FT in which this corresponds to the normal scattering that would accrue from the heavy atoms substituent into the native protein. So this structure factor, the F sub T, would be given as the sum of the structure factor for the native protein plus that for the anomalously scattering atoms. I wanted to see what the connection was between the two. I was sure that there was, because these were exact equations and they were linear, so it had to be essentially the same system. And this is just a definition of unknowns. It turns out that there's a transformation. And as we go on, there are 9 different unknowns that can be so defined if you have 3 different types of structure factor magnitudes: the F1, the F2, and the FT. And these alpha to epsilon are coefficients that occur in the different equations. And this is, as a consequence of the definitions I made, the original equation, that set of equations that I showed you, and here's the one that says sine squared plus cosine squared, or has that inherent in it, is equal to 1. These are the transformation equations that go on to Hendrickson's equations. And they look like this. You see, they're essentially the same. But then there's a new system of equations in which you could combine the F1 and the FT. And this is another transformation that would do that. And this is still a third system. Now, one of the reasons that I did this is that I was wondering whether I could get more accuracy out of using them together or some other property and so forth. In fact, one of my motivations was to look further into initiating one of these calculations by estimating the F1 magnitude. Now, this can be done very accurately statistically. In many circumstances, I wrote a little article on this. I showed that it could be estimated from the measured intensities to even for proteins for less than 2% inaccuracy. And I was hoping that using that as a fixed value would give higher accuracy than I've already obtained in a one wavelength experiment. It didn't turn out that way. I couldn't exceed the accuracy that I had in the first place. I just want to show two more slides of calculations, and then I'll talk a little bit about applications. I still have some time. This is a calculation in which I did something else. I added the consequence of also having an isomorphous replacement associated with the one wavelength experiment. And I put a random error of about 2%, 10% into the magnitude that would come from an isomorphous replacement experiment, the magnitude of the structure factor. And that is what I have called F1. And I tried doing it with 3 equations, the original set, and also 14 equations that come from this extension to different ways of representing the problem. But I only put down one answer here because both answers were essentially the same. And you see that with good isomorphous replacement, that the errors are really very small. There's no point in writing this down to 3 places, but I should have just put it in for 2. But as you can see, in these cases, you hardly exceed 0.2 of a radian. And here, again, with putting in also this error of 0.5 into the difference between the measured magnitudes of the FH plus and the FH minus, why, even then, the errors are really quite small. They don't exceed 25 degrees. But this is not the same calculation as before, because this is a combination of isomorphous replacement and one wavelength anomalous dispersion. And then I have one more slide like this before I talk about applications. There was an improper start. It turned out that when we were making estimates of a calculation that was based on fixing the magnitude of the structure factor for the anomalously scattering atoms, that the table that we were using ran out. And so computers really do have a mind of their own. They made their own estimate, and it turned out to be 55 times greater than it was supposed to be. I don't know, 55 is a good number to bet on or something of the sort. At any rate, this shows that when you make an outrageous start, that there is some virtue in using the 14 equations instead of the 3. As you can see, that when there's this large error factor in the difference between the measured magnitudes, why, this is a pretty bad error in radians for the phase difference, the phi1 minus the phi2. But with the 14 equations, it's almost brought into line. Of course, if you make a proper start, it's very small. Here, when there was no error put into the difference between the measured magnitudes, the error was still very large here, but with the 14 equations instead of the 3, it was quite small. And interestingly, this one turned out to be not the worst this time, with this kind of error in the difference between the measured magnitudes. Even with the 3 equations, it was less than a radian. But the 14 equations, again, brought it into line. And in fact, it was as good as having a proper start. So these are some experiences along those lines. Now, the people who've been actually using this exact linear technique have not been playing with one wavelength or one wavelength and anomalous dispersion. There are a couple of abstracts, actually, here on the program that some of you may have seen. There was a study by a number of people on a cucumber basic protein. And there were people collaborating from the University of Washington, Merritt, and Hauptman, from Stanford, Hodgson and Fazakerly, from Australia, Freeman and Gus, and from Washington University in St. Louis, Lim and Matthews. So that was pretty good. There were 4 different institutions getting practice on the one study. And Hendrickson and his colleagues have also been working with this, as many of you who attended the school or the workshop, at any rate this weekend, would know. And, well, the abstract for this work that was done with Fazakerly and all these other people I mentioned was PD31, and PJ26 is streptavidin, which Palin, Hendrickson, and Satow from the photon factory participated in. Hendrickson and his colleagues have done a few of these. They tried lamprey hemoglobin for practice, and they did ferredoxin, and that was a new one, but they didn't have a good data, and it was turning out like the one that was known, so they didn't pursue it. But then they did an unknown called streptavidin, and if I can just quickly go through this, it comes from it's an avidin protein from a streptomyces. And this is unknown. They started from scratch, and they solved the problem. I'm sorry, this slide isn't very good. These are Harker sections from which they were able to find the selenium atom. The way this was done is that they had a selenium atom attached to biotin, which really sticks to avidin, and the seleno-biotin was the source of the anomalous scattering. And they worked at about 4 different wavelengths. On the left is the first map that they got, and then there are a couple of different molecules in the asymmetric unit, so they did some molecular averaging and improved the map. This is the molecular averaging map, but they also, just to see if they could, were able to work through the structure from this map also. I think it's about a 3 angstrom map, perhaps. One of the people working on it is here, and they could say. This is biotin on the left side, and the way the streptavidin molecules sort of get together in the unit cell. This is a picture of the result. You can see the streptavidin standing out in the structure. It's called a beta barrel. There's just a large number of beta sheets all wrapped around like a barrel to give you the structure. This is another view of it. This really shows that the biotin is sticking deeply inside. Those are 2 carboxyl oxygens that are near the surface of the protein. That's all that really is available from the biotin. There's a picture, Jane Richardson type description. There's a prettier one. And that's the last that I want to show. I want to make one remark. I want to say why I like crystallography. I like crystallography because it permits you to do all sorts of things. You can be a biologist, you can be a chemist, you can be a physical chemist, you can be a mineralogist, you can be a mathematician, and you can have fun, and you can learn a lot of things. I thank you.